The final lesson in topic 2b is called the quadratic formula. In this lesson, we'll still solve quadratic equations, but now with another option. The quadratic formula over on the left-hand side is defined using the quadratic function in standard form. When you're in standard form, remember the coefficients a, b, and c. Those coefficients will help you solve for x using this crazy big formula. So make sure you write that down very carefully, watching your pluses and minuses. It's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So you definitely don't want to write this as a fraction that with a diagonal fraction bar. You want the fraction bar to be left to right, and everything in the numerator divided by 2a in the denominator. Now this is an alternative to solving when factoring doesn't work. You'll have real or possibly complex solutions. And it's going to be super important to be careful when you simplify. Because you're going to be working with square roots and some pretty big numbers, you're going to definitely want a calculator to help guide your work for quadratic formula. Make sure you have all this written out before we start our first example. It says solve using quadratic formula. We have 3x squared minus 4x minus 9 equals 0. So it is a quadratic function in standard form. If we tried to factor and we circled a and c, we would get negative 27. If we try to come up with factors of 27, we have 1 and 27, and 3 and 9. And working together, neither of those would get 4 in the middle. Therefore, factoring doesn't work. That doesn't mean that this isn't solvable, it just means that it isn't factorable. So if factoring isn't an option, we'll try quadratic formula. Our a value is 3, b equals negative 4, and c is negative 9. As we plug these into quadratic formula, we'll start off by saying x equals negative b. So negative, and b is negative, so we have a double negative with the 4. Then plus or minus, and then a pretty big square root. We're going to do b squared, and if b is negative 4, we'll square both the negative and the 4, minus 4 times a times c. So 4 times 3 times negative 9. That's a really big numerator, all over 2 times a in the denominator. Once you plug everything in for a, b, and c, we have to simplify. So we still have x equals. We've got that double negative, so that'll cancel out and make positive 4, plus or minus. On the inside, we have negative 4 squared. That becomes positive 16. Minus, if we do 4 times 3 times negative 9, 4 times 3 is 12, and 12 times negative 9 is negative 108. So notice, again, there's a double negative happening. Now it's on the inside of the square root. In the denominator, 2 times 3 is 6. All right, keep going. We still have 4 plus or minus. On the inside of the square root, minus a negative would become plus. And that means we're going to add 16 and 108. And we're going to get 124 all over 6. From here, I'm just going to give myself a little bit more room. I'm going to make my square root a little smaller. From here, we have to simplify the square root before we reduce the fraction. So simplify the square root first. When we simplify square roots, thinking about numbers that go into 124, we want to try to find perfect squares that go into 124. I know 2 goes into 124, but 62 times, and neither of those is a perfect square. 3 doesn't, 4 does. 4 times 31 would equal 124. So if we rewrite that as 4 times 31, we would get x equals 4 plus or minus the square root of 4 times 31 all over 6. And we can simplify the square root of 4 as 2. So that'll go out in front. That gives us 4 plus or minus 2, but then we still have that 31 on the inside, all over 6. From here, to figure out whether or not you can simplify, we're going to take a look at the 4, the 2, and the 6. So all the numbers kind of on the outside right there. Since they all have a common factor, we can reduce them by a factor of 2. 2 goes into 4 twice, 2 goes into itself once, and it goes into 6 3 times. Notice we're not doing anything else with that 31 on the inside. Therefore, our final answer is 2 plus or minus 1 times the square root of 31 is just the square root of 31. Make that bigger there. All over 3. That's the exact solution for x. With that plus and minus, there are 2 real solutions. Let's try the next one. X squared minus 9x plus 27. If we try to factor, 27 only breaks down into 1 times 27 and 3 times 9 again. Well, neither of those would work to get negative 9 in the middle, so we're stuck once again with quadratic formula. And again, we're just trying to solve for x. So thinking about our a value, technically that's 1, b is negative 9, and c is a positive 27. Here we go. X equals negative b, so we have another double negative happening here, plus or minus big square root, b squared minus 4ac, 4 times 1 times 27, all over 2a, 2 times 1. And now we simplify. We've got that double negative, changes that to positive 9, plus or minus, the square root on the inside, negative 9 squared would be positive 81, minus 4 times 1 times 27, guess what, is 108 again. All over 2. No double negative on the inside, so we'll subtract. We have 9 plus or minus. And now look what happens. 81 minus 108 is negative 27. All over 2. With that negative on the inside, that's going to indicate a complex solution. That means we're going to have to factor the I and put it to the outside. So we'll come down here, x equals, keep the 9 and then the plus or minus, but now put the I on the outside, and then we'll have 27 on the inside, all over 2. Now remember, before we can reduce the fraction, we must simplify the square root. 27 breaks down into 1 times 27, or 9 times 3. And if we think about it as 9 times 3, 9 is a perfect square. So we would have 9 plus or minus I, and then on the inside, 9 times 3, but then all over 2. The square root of 9 is a perfect square, so we'll put that on the outside with the I. The square root of 9 is 3. So again, giving ourselves a spot for the answer here. 9 plus or minus I times 3, or 3i, but then there's still that other 3 on the inside, all over 2. From here, to try and reduce, again, we look at all the parts on the outside. We never reduce the inside of the square root at all. But when we have 9 and 3, but then divided by 2, there isn't a common factor with all 3 numbers. Therefore, our final answer is going to stick. 9 plus or minus 3i times the square root of 3 all over 2. Those are the 2 complex solutions for that quadratic function. A useful tip to figure out the type of solutions or roots that you'll have for your quadratic function is called the discriminant. The discriminant is just the part that's on the inside of the square root. It's b squared minus 4ac. The answer to that discriminant can tell you the type of solutions you'll have. For example, if the discriminant b squared minus 4ac is greater than 0, that means you'll have two real solutions, two actual values on the x-axis where the quadratic function crosses. If the discriminant equals 0, that means the square root would cancel itself out and you only have one solution, and that would be the vertex. Doesn't matter if the quadratic function would open up or down, the vertex would be on the x-axis. And then last but not least, similar to our last example, if the discriminant is less than 0, you have two complex or imaginary solutions. And that means there are no x-intercepts for your quadratic function. So we're going to use the discriminant to describe the type of solutions for the examples on the right. Use the graph to determine the number of roots for each quadratic equation, recalling that roots are the same as zeros or x-intercepts for each quadratic function. Taking a look at our first example, y equals 2x squared minus 7x plus 3. When you look at the picture, you can tell it crosses the x-axis at two locations. But if we didn't have the picture and we wanted to try to solve algebraically to determine the number of solutions, we would use the discriminant. The discriminant formula b squared minus 4ac, if we know what a, oops, I don't want that to be a highlighter. There we go. Let's get rid of that. There we go. We know a is 2, b is negative 7, and c is 3. Following that definition of b squared minus 4ac, notice we're not using all of the quadratic formula, just that inside part. B squared minus 4ac would give us negative 7 squared minus 4ac, 4 times 2 times 3. Negative 7 squared is positive 49 minus 4 times 2 times 3 is 24. 49 minus 24 is positive 25. And that's greater than 0. Because of that, we know it's greater than 0, and that's not even showing up right there. Sorry, that was hard to see. Because 25 is greater than 0, we have two real solutions. So that's showing algebraically that the graph should cross the x-axis twice. All right, let's try the second one. 4x squared plus 12x plus 9. Looking at the picture again, you can tell it's crossing just one time over here on that left-hand side. So let's put b squared minus 4ac to the test. We've got a equals 4, b equals 12, and c equals 9. If we do b squared minus 4ac, we're going to get 12 squared minus 4 times 9. 12 squared is 144. 4 times 4 is 16, times 9 is also 144. And we get 0. Since it equals 0, there's only one real solution. And that's what matches on the picture. I'm guessing you can figure out what happens next. I know, it's very exciting. In our last example, notice the quadratic function has a vertex that's well above the x-axis. So there are no x-intercepts here. To prove that algebraically, we've got a, which is 1, b, which is 2, and c, which is 8. Plugging it into b squared minus 4ac, we would have 2 squared minus 4 times a, which is 1, times c, which is 8. 2 squared is positive 4, minus 4 times 1 times 8 would be 32. 4 minus 32 is negative 28, and that's less than 0. Because of that rule, that means we have two complex solutions, or imaginary solutions. And that's just a useful way that the discriminant can help you when solving these quadratic functions. For now, we're going to skip the discriminant to find a particular equation example and go right down to example 3. Let's end with an application problem that makes the quadratic formula useful for us. We saw this problem earlier in this topic when we were asked to find the maximum height for the baton, and that was simply using the vertex. Here it says, while marching, a drum major tosses a baton in the air and catches it. The height in feet of the baton after t seconds can be modeled by the formula h equals negative 16t squared plus 32t plus 6. If the baton isn't caught, when will it land on the ground? So thinking about what's happening for the path of the baton, if we think about time as our input and height as our output, the baton starts at 6 feet high and it's going to be tossed up in the air. If nobody catches it, it's going to land on the ground, and that would be an x-intercept. To figure out the formula then, we're going to set the equation equal to the height we want it to land at, which will be 0. What we'll do then is take negative 16t squared plus 32t plus 6 and set it equal to 0. Now, thinking about solving, we have pretty big numbers here. How many of you recognize that we have a common factor? We could divide everything by 2, and that would make our numbers smaller on the left-hand side. That would give us negative 8t squared plus 16t plus 3, and on the right we still have 0. We know our a value, our b value, and our c value, so let's plug this in to quadratic formula. What I want you to do is pause the video and see if you can plug everything in, and then we'll simplify together. Notice instead of x equals, I wrote t equals. It means the same thing. Negative b, which would be negative 16, plus or minus the square root of b squared, or 16 squared, minus 4 times a, which is negative 8, times c, which is 3. All divided by 2 times a, which was negative 8. And now we simplify. T equals negative 16 plus or minus the square root. 16 squared is 256 minus, and then we have 4 times negative 8 times positive 3. And that would give us negative 96. All over 2a, which is 2 times negative 8, or negative 16. Be careful here. Do not cross off the negative 16s. We can't reduce that until the very end. So let's keep simplifying. In the inside of the square root, we have a double negative, and that will make that positive on the inside. Negative 16 plus or minus the square root. If we take 256 plus 96, we get positive 352, all over negative 16. But remember, up above in the directions, it said round to the nearest hundredth. So that is going to be useful for us right here. We're going to plug this into our calculator and actually round it to the nearest hundredth. If you take the square root of 352, we get approximately 18.76. So then we're going to do a squiggly equals, because it's not exact any longer. Negative 16 plus or minus our approximation 18.76 all over negative 16. From here what we'll do, and this is why you'll definitely want your calculator. I'm going to give myself a little bit more room first. Slide this over. I know it's a little crooked. There we go. That's about as good as that's going to get. So we'll branch this out into 2 choices. We'll split apart the plus and the minus. We'll do negative 16 plus 18.76 and divide it by negative 16 and get an answer. And then we'll do negative 16 minus 18.76 divided by negative 16, and we'll get an answer. We'll have 2 choices here, and we'll need to decide which one makes the most sense. If we type in negative 16 plus 18.6 or 76, we get 2.76. But if we divide that by negative 16, I'm doing that as I write here, I get negative 0.17. So we'll see how that holds up when we're done with our final answer. The second one, if we take negative 16 minus 18.76, we get negative 34.76. And if we divide that answer by negative 16, 34.76, divided by 16, we get approximately 2.17. So those are our two choices, everybody. A negative answer. Whoops, I don't know why I scribbled that out. Sorry. Let's try that again. Sorry, I'm taking so much time up doing that. I didn't mean to scribble that out. Negative 0.17 or 2.17. I meant to grab the highlight option. There we go. So we've got that negative time and a positive time. Which one would make sense to actually land on the ground? Definitely the positive time. So what that would indicate is that that negative solution isn't valid. So therefore, up at the top, we'll say it takes approximately, do the squiggly equals, 2.17 seconds for the baton to land on the ground if it isn't caught. And that is lesson 2.6.